Hi, my name is Julie Luttrull, and today I'll be presenting on the paper Overshadow PLC to detect remote control logic injection attacks. I would like to note this is not my own research and I did not write this paper nor contribute to it. However, I do work as a process control engineer, and I do find this research quite interesting as I maintain PLCs and other control equipment that is vulnerable to the attacks discussed here in this paper. Here are the paper's authors. They were from the University of New Orleans, Oak Ridge National Laboratory, and Virginia Commonwealth University. So the way I'll be presenting this paper today, I'm going to give you an overview of what the problem is and the motivation of this research. After we discuss that, I will be discussing the solution that the authors proposed, which is called SHADE, and we'll be going quite a bit more in depth with that. We will also be discussing how SHADE functions and how they have made this work and made it so successful. And then we'll be discussing the results of the study. The problem that this paper is discussing is that there have been two new forms of logic injection attacks that have been recently developed. The first of these is a data execution attack, and the second is fragmentation and noise padding. These are quite troubling because PLCs are very vulnerable to these due to the fact that packet header signature and payload inspection do not capture either of these particular attacks. The way a data execution logic injection attack works is that this malicious actor puts code into the actual data blocks of the PLC, and that PLC uses those data blocks usually to transfer sensor data to and from the PLC. So a data execution attack inserts the code into the data block, and then once this compiled logic is inserted, the attacker moves the pointer to activate their code. So one thing to note about PLCs, if you're not quite as familiar with them, is that when you are completing this command code and you're trying to talk back to some process to make it do something, sometimes you have analog signals like a temperature, which might be a 4 to 20 milliamp signal coming back to your PLC, telling you at 4 milliamps, maybe your temperature is at the low end, which let's just say that's 32 degrees. At 20 milliamps, maybe that's 100 degrees. You have some sensors like that will talk back to the PLC in that way. You might have other sensors that are actually a little bit more advanced that are going to send back packets of data. And those packets of data that are coming back to the PLC, a lot of times are going to get processed in something like a data block. So that's the reason that we have these data blocks, is they process these other communication techniques that have more data. Something like a power sensor, instead of communicating 4 to 20, it actually might send back quite a bit of data saying, this is my power, this is also the status of the relay, and different things like that. It's very handy because we can get a lot of data back to the PLC. But as we can see here, it's also problematic because now it's much more vulnerable to something like a 4 to 20 milliamp signal coming back to the PLC. The second attack style here that's discussed is a fragmentation and noise padding attack. The way this works is that the attack actor breaks up the payload into very small chunks. Usually it's 1 to 2 bytes in length. They then pad this payload with a bunch of random data, and this is their noise. So the attacker makes a header, and the packet doesn't actually copy the noise to the PLC. So whenever you're doing packet inspection, you won't see anything malicious. You'll only see 1 to 2 bytes that actually are malicious, but the PLC itself only sees those 1 to 2 bytes, and later that's turned into an actual command by the PLC. So now if you imagine actually combining these two attacks, what now you would get is a PLC would see what looks like just a bunch of really random, really noisy sensor data coming back to it. In reality, this very noisy sensor data that's coming into, say, this block would actually be something like a fragmentation and noise padding attack. So you could actually combine these two things to successfully attack this PLC in a way that's extremely hard to detect because it looks very organic, when in reality it's an attack, it's not organic. So the issue with this is that deep packet inspection can't actually prevent these attacks. So since PLCs read and write so much data between these sensors using data blocks, deep packet inspection isn't going to flag that malicious code because it just looks like normal sensor data coming to and from the PLC. Deep packet inspection also can't see whenever you fragment up your code like that, it's not going to see it because it's only inspecting the packets. It's not inspecting the actual memory of the PLC. So even though the PLC sees a large chunk of code that is malicious, the packet itself looks quite benign. And you can actually combine both of these attacks and successfully trick these signature-based approaches into not recognizing this malicious code at all. So the solution that this paper proposes is called SHADE. The authors made this code that can detect these types of attacks. So SHADE makes a shadow copy of the PLC's memory. It scans the data that's going to and from the PLC, and it can also then decompile it for review. So instead of scanning the individual packets, it takes all of this data that it's been able to decompile and scan, and it makes it into its own copy of what the PLC memory looks like based on that traffic. It then uses 42 different features that it collects, and it can categorize them into 5 different levels of control code. So what exactly is SHADE's shadow memory? So what that is, SHADE's memory is a copy of the protocol address space of the PLC. This address space is all of the space that can be addressed for the data through the PLC. So when a read or write request is made through the PLC, Shadow then collects this and recreates it into what the PLC memory should be. It can then inspect the recreated memory rather than actually having to inspect the packet itself. So it can do this as a more holistic view instead of just seeing one packet at a time. So this is an illustration of what the shadow memory looks like, where X is your address, N is the length, and B is the scan boundary, and M is your highest address in the memory. So your max scan area is from 0 to X minus B, which is your address minus your scan boundary. Your minimum scan area is M to X plus N plus B, so your highest address in memory to your address plus your length plus your scan boundary. So the smaller that the scan boundary is, the less overhead and the fewer false positives you're going to have. And the higher that B is, the higher the sensitivity. This is quite important, and later we'll discuss the results of varying that B. But the reason it's so important is that your overhead will be very important here, because the quicker that you alert the person that something is wrong, the quicker that you can actually respond. And in these situations, that's going to be very important. But the issue is, if you have a lot of false positives, this isn't like an IT device, like a laptop, where if you have a false positive and you have to wipe that device, it's not really a big deal. If you have a false positive on a PLC saying there's something malicious and you take action on that, that can cause downtime to machines and other really detrimental things. So false positive here is very problematic, and you really need to minimize that as much as possible. So a higher B is going to give you higher sensitivity, but you're going to have a lot more false positives. SHADE works by extracting several different features out of the shadow memory. So on one end of the spectrum, you need very high level of semantic knowledge, and that's for things like your full decompilation. And on the other end of the spectrum, you need no semantic knowledge at all for things like your engram or your entropy. So on your high end of the semantic knowledge spectrum here is your full decompilation. So this is unique to PLCs because unlike codes written in Java and C and other languages like that, control code can be completely decompiled into its source code by seeing this network traffic. So ladder logic and other PLC codes can actually be mapped one-to-one with its compiled codes sometimes. Different PLCs have different levels of this, and especially in this situation, Modicon was actually a lot easier to decompile than the Control Logic's PLC was. And SHADE actually can count the number of decompiled bytes. So if it's something like this Modicon PLC, it can decompile everything and it'll count all of those. And if it's something like the ControlLogix PLC, it may only be able to do partial decompilation. So as you can see here, this is an example. In this situation, on the left, you have the Modicon M221 PLC. So it can see on the very far left side of this message that it has a normally closed, and then an and then another normally closed, and then we have an OTE, which is your end of rung, your output, and then another XIC, and then you have another end of rung message. So that can actually be one-to-one translated to actual ladder logic code. On the other hand, you have the MicroLogix 1400 PLC. Here you actually have some partial decompilation going on. Here you can see that where it's the variated line there, that DA4F and different things like that. Those are actually code that the PLC itself, you would have to have the actual ControlLogix code to completely decompile that. Those are timers there, and they do require some extra semantic knowledge. So in this case, you actually can't fully decompile that, but what Shade does is it just counts that timer as one decompilation. So even though it can't fully decompile it, so it's kind of a bit of a black box to Shade, it doesn't really matter because in this situation, it just knows that it's a timer. Two other features that Shade uses is opcodes and rungs. So Shade maps the opcodes, and those are operational codes, into a table and counts the number in each scan area. It identifies these codes based on a table that the authors created that maps the instructions to different low-level codes. They also count the number of rungs, and they do that by using the same address signatures, and they indicate the beginning of different rungs. So MicroLogix has one set of addresses it uses, and other PLCs have different addresses that they use to indicate the beginning of a rung. The last set of features that Shade uses is engrams and entropy, and these are at the very low end of the semantic knowledge spectrum. So engrams extract different features with absolutely no semantic knowledge, and this is a method that they typically use in language processing fields. Shade counts how many times the engram is present, and it also counts the number of times that engrams are part of a predefined set of engrams. So they use these two different engram methods. The other thing that it calculates is the entropy, and it calculates that based on a Shannon entropy, and that's on the byte level. Once all of these different features were collected, then they needed to analyze them using machine learning. So here they used two different machine learning tactics. The first was a Gaussian naive Bayes method. The second was a support vector machine method. And as you can see here with the results, both machine learning methods gave about the same results, other than at the very far left hand of the graph, which is for our very low false positives, we had a slight difference in the two methods. But across every single test that they did, if you notice at the very bottom of that graph, that bottom line with the circles represents trying to use a packet-based detection method. And across every single test, that detection method didn't have any true positives using the set of data that they were testing it against. But you actually had very good results using the Shade method here, using these features. Here we can see an overview of Shade's performance. We'll be going further into depth about the reasons for these different values. But as you can see here, at the top we have a detection rate for our Modicon, which is an M221 series. After that, we have our detection rate for our MicroLogix 1400. As you can see, with your package-based DPI, you actually had a 0% detection across the board there, whereas at the high end of the spectrum, we actually had a 97.52% detection for the Modicon. For the MicroLogix, you have a 95.68% detection, which is astronomically high. Also, under that, we have the performance according to our scan boundary and how B actually affects your result for both your Modicon and for your MicroLogix PLCs. It is important to note that overall, Shade performed very well in all of these tests. Even though fragmentation with padding is very hard to detect on a packet level, it is very much detectable in the PLC's memory. the malicious packets get reconstructed into the PLC memory, and the noise is already removed once it gets to the PLC memory. So similarly, code sent via data blocks will be reconstructed in the PLC's memory as recognizable commands. So because of this, since Shade uses a shadow memory approach, it actually performed very well against both of these attacks. So after testing with all the different features, the study found that engrams combined with decompilation provided the highest detection rate. Engrams were the most effective standalone feature for the M221 PLC, which was your Modicon, and the L-engram was more effective standalone feature for Micrologic. So your engram is your the number of engrams that are present in the Bloom filter, whereas your L-engram is the longest continuous match of engrams that are present in the Bloom filter. So it's a little bit different between those two, but they were the same general approach. And this seems kind of odd because when you think about it, your engrams are what use the most low-level semantic knowledge. So you would expect these generally to actually be less accurate. As we can see here in our approach at the top, you can see the Modicon. Using just your engrams, you actually had a 95% detection rate of your packets, as opposed to just using deconstruction, you only had about a 92.23% detection rate. Still quite good, not quite as good as using engrams. Similarly, for your micrologics, this is where you actually see a larger difference. For deconstruction, you only had about a 92% attack detection rate, whereas with engrams, you actually had a 93.9% rate. And this, again, it seems kind of odd because you don't need near as much semantic knowledge. In fact, you don't need any semantic knowledge. So why would this happen? The reason this happens is that there are certain byte patterns, like for the micrologics, 0000 is a pattern that does show up every once in a while. That pattern isn't recognized correctly by the detection method where you decompile things. It can't quite recognize the length that it's supposed to see there because of that 0000, and therefore it doesn't actually correctly decompile that following instruction. So because of that, you get some false decompilations, and that does cause that to not be quite as accurate as you would actually expect it to be. So the authors here found that combining those two methods gave you the most accurate results. For the Modicon, it was around a 97.52% detection rate, which is astronomically high. And for the Micrologics 1400, it was a 95.68% rate. And that is opposed to packet-based detection, which across all of these tests was a 0% detection rate. Another very interesting aspect of the study was how you can vary B, which is your boundary, and manipulate your results a little bit. So B is that boundary length. The greatest that boundary length could be for that particular PLC for Modicon was 236 as your maximum. For your Micrologics 1400, that was actually 80. So this actually applies more to the Modicon than it does the Micrologics. There's a little bit more variance here. But in the case of the Modicon, with that maximum boundary, you had a 93.69% attack packet detection, which is very high, and that's very good. With Micrologics, it's 94.25%, which is extremely high, very good. The issue, though, is your overhead in the case of the Modicon was actually 31.92%, which means things are going to process much slower. Also, something else to note here, your false positive rate is going to be much higher in this scenario. They don't actually have that here in the data, but they do note that. So because of this, that can be quite a big problem, as we discussed earlier. If you reduce B, you're actually going to reduce your false positive rate. Also, you're going to reduce your overhead substantially in the case of Modicon. So as you can see here, if you reduce B to equal to 6, you're actually going to only have an overhead of 2. Vanya. In conclusion, Shade was extremely successful at detecting a combination of data fragmentation attacks as well as logic block execution attacks. This particular packet inspection method worked when other methods would have failed and had a 0% success rate according to this particular study. And it's also very important to note that shade had a very low false positive rate, which, as we discussed before, is very important because a false positive in this situation, it can be quite detrimental to a system. If you have any questions or comments about this research or this presentation, please feel free to contact me via the contact information there or comment below.